Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Thanks for having me back.
So I want you to imagine this scenario. You are standing in a massive, hyper-clean assembly bay, right?
Okay, setting the scene.
Yeah. And above you is a payload fairing. It's preparing to close over this state-of-the-art communications satellite. I mean, this is a massive aerospace project where the launch logistics alone costs $10,000 a pound.
Wow.
Right. Every single gram has been optimized. Every subsystem has been meticulously modeled. And as the technicians move in to, secure that final mating bracket between the solar array deployment mechanism and the main chassis.
I guess the bolts don't align.
Exactly. The holes are off by a fraction of a millimeter. The pin just will not seat. And you can't just grab a hand drill and bore out the hole on a flight-ready spacecraft.
Oh, absolutely not. You'd be fired on the spot.
Right. So you are entirely dead in the water. You're bleeding hundreds of thousands of dollars a day in delays, all because two pieces of metal manufactured on opposite sides of the country, mind you, simply refuse to fit together.
Yeah, I mean, that is the ultimate nightmare scenario for literally any project manager or design engineer. And unfortunately, it happens far more often than the industry really likes to admit.
Oh, I bet.
And that's exactly what we're looking at today. We've got a really interesting stack of sources that address this exact pain point.
Yeah, we've got some heavy hitters today.
We do. We're looking at a highly detailed tolerance analysis report from Boeing Research and Technology, authored by Fritz Schultz. That one really digs deep into the statistical mathematics of how parts stack together.
The heavy math.
Exactly. Plus, we've got some very practical sourcing and manufacturing guidelines from Xometry, and we're also taking a look into the historical evolution of NASA and ASME engineering drawing standards. And the overarching theme across all these documents is just the brutal physical reality of manufacturing variation. And, the mathematical language we have to develop to control it.
Right. And that language is geometric dimensioning and tolerancing, universally known as GD&T.
That's the one.
Along with what I like to call the dark art of tolerance stack analysis. Because whether you are a seasoned mechanical engineer who spends, 8 hours a day detailing CAD models, or you're someone adjacent to manufacturing like in quality control, procurement, or even project management.
Right, anyone touching the hardware.
Exactly. Understanding the why and how of this topic is basically your ultimate shortcut. It is the shortcut to avoiding that exact Houston, we have a problem moment on the assembly floor.
Precisely. Because when you are dealing with mass manufacturing, or like you said, high-stakes aerospace, where you're paying $10,000 a pound for orbit insertion perfection, is just a physical impossibility.
Right. You literally can't make a perfect part.
You can't. The machine tools wear down. The temperature of the cutting fluid fluctuates during the day. The metal itself literally springs back a little bit after it's been machined.
Oh, right. Internal stresses.
Exactly. So you just cannot demand perfect parts. What you must demand, and what GD&T actually allows you to achieve, is parts that are perfectly understood within a really highly specific framework of allowed imperfections.
Allowed imperfections. I like that.
Yeah, and to truly understand why this framework is so incredibly rigid today, we actually need to strip away the modern CAD software for a minute and look at how this problem almost broke the industrial supply chain completely.
Oh, I'm glad you brought up the history, because there is this massive common misconception I hear, especially from junior designers.
Oh, what's that?
Well, they think GD&T is just like an academic exercise. Like it's something a group of grumpy mathematicians dreamed up just to make reading blueprints harder for everyone else.
Right, like it's just busy work.
Exactly. But it was actually born out of sheer panic, wasn't it?
Absolute panic. I mean, if you rewind to the mid-20th century, specifically during that massive scale-up of military and industrial production surrounding the world wars, the whole nature of manufacturing fundamentally changed.
How so?
Well, before that, a lot of complex machinery was built under one roof. The machinist making the piston was literally in the same building as the machinist making the engine block.
So they could just talk to each other.
Exactly. If a piston was a little tight, they just walked across the shop floor and figured it out with some sandpaper or a file and fitting.
Okay. Yeah.
But mass production completely decentralized that supply chain. Suddenly, the pistons are being cast in Ohio, they're being machined in Michigan, and the engine blocks are coming from Pennsylvania.
So they were completely relying on traditional engineering drawings to communicate between these states.
Yes. What we now call CD&T, or coordinate dimensioning and tolerancing.
Right. the old school basic dimensions.
And CD&T proved to be catastrophically inadequate. The defective parts problem became astronomical.
Wow, really?
Oh yeah. The military and the industrial sector were receiving thousands of parts that perfectly matched the numbers written on the drawing, but completely failed to assemble in the field.
Wait, how is that possible? If the numbers matched, why didn't they fit?
Because they realized that a basic 2D drawing with standard linear tolerances simply does not reflect the actual functional relationship between mating parts.
Okay, wait, let's dig into why that traditional CD&T drawing fails so spectacularly, because I feel like this is where the illusion of the blueprint really falls apart for people.
It really does.
So let's say I'm a junior engineer, right? I open up my CAD software and I draw a simple rectangular block.
Okay.
And I put a hole in it. I use the basic dimension tool to say the hole is exactly 2 inches from the left edge, and I type in a tolerance of plus or minus 0.05 inches.
A classic CD&T call-out.
Right. To my mind, I have done my job perfectly. I gave the machinist a target, and I gave them a mathematical boundary. Why is that an illusion?
It's an illusion because your CAD software exists in a perfect theoretical universe, and that physical piece of aluminum sitting on the milling machine simply does not.
Okay, fair point.
The misconception there is that those standard linear tolerance zones, that little plus or minus box you typed in, actually define the real-world geometry of the part.
Wait, they don't?
They do not. Traditional CD&T only gives you a linear distance between two theoretical points. It completely ignores the actual form, the overall shape, and the physical orientation of the feature.
Wait, break that down for me. If I take my calipers and I measure 2 inches from the edge and it says 2 inches, isn't that the whole story?
Not even close. Let's look at your rectangular block.
Yeah.
You measure 2 inches from the left edge, right?
Yeah.
But is that physical left edge perfectly straight? In reality, it's going to have microscopic hills and valleys from the end mill that cut it.
Oh, sure. Surface finish.
Right. It might be slightly bowed. It might not be perfectly perpendicular to the bottom surface. So when the quality inspector places their measurement tool against that edge, which microscopic hill are they referencing?
Oh, I see.
Are they measuring from the top corner, the bottom corner, or the middle of the bow? Your simple plus or minus tolerance provides absolutely no clear frame of reference for how the part actually functions in an assembly.
Or how it has to be physically oriented to be inspected. That makes total sense.
Exactly.
Actually, the source material has a brilliant concrete example of this breaking down. They show a drawing of a flanged cylindrical part.
Oh yeah, the top hat example.
Right, imagine a top hat. You have a central hole going all the way through it, a raised hub in the middle, and a wider outside diameter flange at the bottom.
Got it.
And the drawing calls out this small slot cut into the outer edge of the flange. It gives a dimension for the location of that slot with a tolerance of plus or minus 0.4 millimeters.
Seems simple enough.
Right, it looks completely unambiguous on paper.
But on the factory floor, it is an absolute nightmare. The question immediately becomes, what is the origin of that dimension? Where is the 0, 0 coordinate?
Exactly.
Is that plus or minus 0.4 millimeters measured from the center axis of the inner bore? Is it measured from the center axis of the raised hub? Or is it from the center axis of the outside diameter flange?
And see, in my perfect CAD model, all three of those axes are perfectly concentric. They share the exact same mathematical line in digital space.
They do.
So as the designer, I don't even think to specify which one, because to me, looking at the screen, they are all the exact same thing.
Precisely.
Yeah.
But when a machinist chucks that piece of raw steel into a lathe, turns the outside diameter, then physically flips the part around to bore out the inner hole, tiny amounts of runout and variation are introduced.
Oh, because they reclamped it.
Exactly. The inner hole, the raised hub, and the outside flange will all be slightly eccentric to one another. Their physical center axes will be scattered by fractions of a millimeter.
Wow.
So when the quality inspector tries to verify the location of your slot, their measurement depends entirely on which physical feature they use to establish their center point.
So if they use the inner bore as 0, the slot might pass inspection.
Yep. And if they use the outer flange, it might fail. And the CD&T drawing doesn't tell them which one is the functional requirement for the assembly.
And this vacuum of information is exactly what breeds what the sources call tribal knowledge.
Oh, tribal knowledge.
Yeah.
The enemy of mass production.
Because the drawing is fundamentally ambiguous, the quality inspector literally has to stop what they're doing, walk across the facility to the engineering department, track down the original designer, and ask, hey, when you drew this slot, What did you actually intend for it to line up with?
which is just a complete system failure.
Sure.
An engineering drawing, or a modern 3D model data set, is supposed to be a legally binding contract between the customer and the supplier. If that contract is based on tribal knowledge, like on one guy remembering a conversation he had with another guy 3 years ago over coffee, you have no legal recourse when the parts show up and do not fit.
Because under those ambiguous CD&T rules, a supplier can manufacture a part that technically meets their valid interpretation of your vague drawing.
Even if it's completely useless in your final assembly.
Exactly. And because they technically met the dimensional numbers on the page, you, the customer, have to foot the bill and pay for the scrap.
Yep. It makes me think of an analogy. It's kind of like trying to scale up a family recipe.
Oh, I like this. Go on.
Say my grandmother writes down, add a pinch of salt and bake until the crust is golden brown. That works perfectly in her kitchen because she possesses the tribal knowledge.
Great. She knows her own kitchen.
She knows the exact humidity, she knows her specific oven runs hot on the left side, and she knows exactly what golden brown means to her eyes.
But if I take that exact piece of notebook paper, hand it to a massive automated commercial food factory, and ask them to produce 10,000 pies a day.
It's a total disaster.
Right. One factory shift manager's pinch is 20 grams, another's is 5 grams. And golden brown, under harsh LED factory lights, looks completely different than in a sunny home kitchen.
That is exactly the dynamic. GD&T is the engineering equivalent of eliminating the pinch and the golden brown. It replaces vague visual instructions with mathematically undeniable parameters.
So instead of bake until done,
It states bake at a sustained ambient temperature of 350 degrees Fahrenheit for exactly 42 minutes, verified by an internal thermal probe calibrated to NIST standards.
that is perfectly clear, no tribal knowledge needed.
Exactly. GD&T uses a standardized vocabulary, highly specific rules, and mathematically defined symbols to create a legally indisputable definition of the physical part.
Okay, but wait. If GD&T is this perfect, indisputable, internationally recognized standard, why are there still so many arguments on the shop floor? Because reading through the sources, specifically looking at how different regions apply these rules, it seems like we just traded one set of problems for another.
You're not entirely wrong.
Like, we agreed to stop using the grandmother's recipe, but now half the factory is speaking French and the other half is speaking German, and they don't even realize it until the parts crash into each other.
You are hitting on one of the most insidious and frankly expensive pain points in modern global manufacturing.
The language barrier.
The global language barrier. We have two primary global standards that look incredibly similar on the surface. They literally use the same visual symbols, but they operate on fundamentally different mathematical philosophies deep down.
And we are talking about the massive divergence between ASME Y14.5 and ISO 1101, right?
Exactly. ASME Y14.5 is heavily utilized in the United States and by many massive multinational aerospace and automotive corporations, while ISO 1101 is the dominant standard across Europe and parts of Asia.
But how bad could the divergence really be? I mean, a circle is a circle, right?
You would think so.
The sources highlight a specific timeline that maps out what we can call the 65% problem, and the numbers are frankly terrifying if you manage a global supply chain.
The historical drift between these two organizations is startling. If we look back to 1994, one of the great pioneers of this field, Lowell Foster, published a definitive textbook called Geometrics Thur.
Okay.
At that point in time, Foster evaluated the two systems and claimed there was roughly a 90 to 95% agreement between the ASME standard and the ISO standard.
So they were basically identical.
They were on a path toward global harmonization.
Yeah.
A mechanical engineer in Detroit could send a drawing to a CNC machinist in Munich, and they would both interpret the symbols almost identically.
But then we fast forward. The sources bring up Alex Krulikowski's 2010 book, ISO Geometrical Tolerancing, and the entire landscape has fractured.
Fractured is the right word.
Krulikowski's analysis states that roughly 65% of all possible tolerancing specifications are now either specified differently or interpreted differently between ASME and ISO.
Yep.
Wait, really? We went from 5% disagreement to 65% disagreement. How does a global technical language devolve that quickly?
It wasn't really a devolution, it was a philosophical divergence in response to rapidly advancing technology.
What do you mean?
Well, as manufacturing capabilities and coordinate measuring machines became exponentially more precise, the two standards committees had to decide how to mathematically define increasingly complex geometry.
Okay.
They kept using the same visual symbols on the drawings. A circle with a crosshair for position, two concentric circles for concentricity. But the underlying software algorithms they wrote to verify those symbols took completely different paths.
I need to understand the why here. Why did they take different paths? Is it just stubbornness, or is there a functional reason behind it?
It comes down to what each standard prioritizes fundamentally.
Hmm.
ASME Y14.5 is heavily influenced by the concept of the perfect functional boundary.
Functional boundary, okay.
It is deeply rooted in the idea of assembly. It asks, if I have a pin and a hole, what is the absolute worst-case envelope of that pin, and will it physically slide into the hole? It thinks in terms of 3D mating envelopes.
Well, it's very practical. Will the parts go together?
Exactly. ISO 1101, on the other hand, evolved with a strong philosophical focus on independent geometric elements.
Meaning what, exactly?
It tends to look at the isolated surface or the derived theoretical axis of a feature separate from how it interacts with the rest of the part. It's a more purely mathematical approach to the geometry itself.
Okay, let's look at how that philosophical difference actually ruins a part on the factory floor. Give me a concrete example.
Let's take the concentricity symbol. It's two circles inside each other.
Right. So let's say I'm designing a high-speed spinning shaft. It has a thick middle section and a thinner end section, and I need them to share the exact same center point so the shaft doesn't vibrate itself to pieces at 10,000 RPM.
Okay, perfect example.
I drop the concentricity symbol on the CAD drawing. How does an ISO inspector evaluate that versus an ASME inspector?
If the drawing is governed by the ISO 1101 standard, that concentricity symbol strictly commands the inspector to evaluate the derived central axis of the feature.
So they just find the middle line.
Basically, they will probe the surface of the thinner section of the shaft, use the software to calculate the theoretical central line running down the middle of it, and then check if that invisible line falls within the allowed tolerance zone relative to the thicker section. ISO primarily cares about the theoretical spine of the part.
Okay, that makes perfect sense mathematically. So what does ASME do?
Under ASME Y14.5, that exact same visual symbol requires an entirely different physical measurement process. ASME concentricity controls the opposed median points of the feature.
Opposed median points.
Yes. To inspect it properly, the quality technician cannot just calculate a central axis. They have to map out thousands of distinct points exactly opposite each other on the circumference of the shaft.
That sounds intense.
It is. They take point A on the top and point B exactly 180 degrees across from it on the bottom, and they find the exact midpoint between them. They have to do this all the way around and all the way down the shaft.
Wow.
They create a cloud of median points, and every single one of those microscopic points must fall within the tolerance zone.
That sounds incredibly tedious. Why would ASME require that?
Because of rotational mass. If a shaft is slightly lobed, say it is shaped a tiny bit like a triangle instead of a perfect circle, its theoretical central axis might still be perfectly straight.
Oh.
Exactly. ISO would pass it. But if you spin that triangular shaft at high speed, the unbalanced mass on the outside will cause massive vibration.
Right, because the weight isn't distributed evenly, even if the center line is straight.
Precisely. By forcing you to measure the opposed median points, ASME concentricity inherently controls both the center location and the balance of the mass distribution. It is a much stricter, more functional control for high-speed dynamic parts.
That's a huge difference. So if your supplier uses an ISO CMM program to measure an ASME concentricity callout, they will just check the axis past the load shaft.
And your assembly will tear itself apart on the test day.
Man, that is terrifying. And this brings up another critical divergence from the sources, specifically regarding how we just measure basic size, just the simple diameter of a pin.
Yes. Rule number 1.
Right. In ASME Y14.5, a size tolerance inherently controls two completely different things at the same time, right? The local size and the actual mating size.
Correct. Under ASME, we have a foundational concept often referred to as rule number 1, or the envelope principle.
The envelope principle.
When you specify a size tolerance for a feature of size, like a cylinder or a slot, you are simultaneously defining a perfect boundary that the part cannot violate.
Okay, so if a pin has a diameter of 10 millimeters, plus 0 minus 0.1.
The ASME rule states that the pin can never at any point violate a perfect theoretical cylinder of exactly 10.0 millimeters.
So I take a micrometer, which measures a 2-point local size, and I measure 9.9 millimeters everywhere on that pin. It passes the local size check.
Yes, the cross-section is good.
But if that pin was accidentally bent in the machine so it looks like a banana, it might not physically fit through a perfect 10-millimeter hole.
Exactly. Because of rule number 1, ASME says that banana pin is defective. even though every single 2-point micrometer measurement was technically within the tolerance band.
The perfect form at maximum material condition acts as a rigid, unyielding envelope.
That's it, exactly. But here is the trap. ISO 1101 does not operate with the envelope principle by default.
Wait, really? ISO will just let the banana pin pass?
Yes. In the ISO system, by default, a size tolerance only controls the 2-point local size.
That's crazy.
It only cares what your micrometer says when you pinch the part. It does not automatically guarantee that perfect outer bounding envelope.
So how do you ensure the bent pin won't get shipped to you?
If you want to force the supplier to ensure that the bent pin will actually fit into a mating hole, you have to explicitly add an additional symbol to the drawing.
What symbol?
An E with a circle around it, which stands for the envelope requirement. If you, as an American engineer used to ASME defaults, send a drawing to Europe without that circled E, you are legally authorizing them to ship you banana-shaped parts as long as the cross-section measures correctly.
Wow. This feeds directly into a massive operational hazard the sources highlight, which they call the danger of wrong is best.
Yes, wrong is best.
It's such a strange phrase. What does that actually mean in the context of a quality control lab?
It refers to the terrifying illusion of precision created by modern coordinate measuring machines, or CMMs.
Right, those massive robotic arms in the glass rooms.
Exactly. They are incredibly advanced robotic systems. They use a ruby-tipped probe to physically tap the part thousands of times, generating a digital point cloud with microscopic precision.
So the machine itself is flawless.
The machine is flawlessly accurate, but the danger lies in the invisible software algorithms processing that point cloud.
Because the software has to be told which mathematical dictionary to use.
Precisely. CMM software packages are developed for a global market. You might be a machine shop in California, inspecting a part explicitly designed to the ASME Y14.5 standard. But deep in the settings menu of the CMM software, the default evaluation math is set to ISO 1101.
Oh no.
The robot measures the part perfectly, the software crunches the numbers perfectly, but it uses the ISO algorithm for something like position or profile. The screen lights up bright green, big, bold letters saying pass.
And the machinist celebrates, packs the parts in a crate, and ships them.
Yep. But the evaluation was fundamentally mathematically wrong according to the legal contract of the drawing.
It is the ultimate false sense of security. You have a $500,000 piece of metrology equipment lying straight to your face because of a hidden drop-down menu.
Exactly.
So what is the hard takeaway for the listener here? How do you defend against this?
You have to become absolutely militant about the dialect. First, the specific standard and its revision year must be explicitly stated on the drawing or in the model's metadata, for example, tolerances per ASME Y14.5 2018.
You can't just assume they know.
Never assume. But that is not enough. You must actively audit your supply chain and your internal quality labs. You have to sit down with the CMM programmers and verify visually that their measurement software is explicitly toggled to the exact same standard the engineers designed to.
You have to police the mathematics.
You cannot assume harmonization. You have to police the math.
Okay, let's assume we have done the hard work. We picked a standard, we audited the software, everyone is speaking the exact same dialect of GD&T, and there are no banana-shaped pins sneaking through.
A perfect world.
Right. How do we actually use this language to guarantee that these parts assemble smoothly on the factory floor? This brings us to the physical reality of fits and the fundamental concept of the datum.
This is where we transition from avoiding disasters to actually engineering functionality.
Right.
The Xometry sourcing guidelines provide an excellent breakdown of this. The entire goal of GD&T in a mass production environment is interchangeability.
Interchangeability. So basically making sure any part fits any other part.
Exactly. It means manufacturing part A in January, manufacturing part B in June, pulling them both blindly out of a warehouse bin in December, and knowing with absolute mathematical certainty that they will fit together and function identically to every other assembly.
And the sources make a really great point contrasting this with the traditional craftsman.
Oh yeah, the rocking horse example.
Right. If I am a master woodworker building a custom rocking horse, I don't need GD&T. If I turn a wooden peg on my lathe and it's a little too thick to fit into the hole on the rocker, I don't calculate the geometric deviation.
You just fix it.
I just grab some sandpaper and manually widen the hole until it slides in perfectly. I'm custom fitting every single joint. I have the luxury of iterative adjustment.
But mass production strips that luxury away.
Completely.
In mass production, you do not have the craftsman's sandpaper. You cannot rely on hand fitting because it completely destroys the assembly line's throughput. Instead, you rely on calculated, standardized fits.
And the Xometry guidelines categorize these into two primary operational modes, right? Clearance fits and interference fits.
Yes, and the math behind each dictates entirely different manufacturing approaches.
Let's unpack the clearance fit first. Functionally, it is exactly what it sounds like. It's an assembly designed so that you do not need heavy tools to force the parts together.
Right. It should assemble freely.
A clearance fit can range from incredibly loose, like a heavy steel bolt dropping easily through an oversized bracket hole, to a highly precise, lubricated slip fit, where you slide a ground piston into a cylinder bore by hand, and you could actually feel the air pressure resisting you because the gap is so microscopic.
But the defining characteristic is that there is always mathematically a gap.
Yes, and to guarantee that gap, we have to look at the extremes of the manufacturing tolerances, specifically a concept called maximum material condition, or MMC.
Let's pause and define MMC clearly because it trips up a lot of people.
Let's do it.
When we say maximum material condition, we are talking about the physical state where the part weighs the most, right?
Right. So for a solid pin, MMC is the absolute largest diameter the tolerance allows, because a fatter pin has more metal.
Exactly. But for a hole, MMC is the absolute smallest diameter allowed because a smaller hole leaves more physical metal in the surrounding block.
Oh, that's a great way to remember it.
That is a perfect explanation. It is the condition that leaves the maximum amount of material on the part. Now, for a clearance fit to be mathematically guaranteed, you must design the tolerances so that the MMC of the internal part, the absolute fattest, largest allowed pin, is strictly smaller than the MMC of the external part, the absolute tightest, smallest allowed hole.
So if you design the tolerances so that the fattest possible pin is still mathematically smaller than the tightest possible hole, you have guaranteed a clearance fit no matter where the actual manufactured parts fall within their allowed tolerance bands.
Exactly. It is playing it safe by looking at the worst-case scenario.
Now, contrast that with the interference fit. This is where the engineering gets aggressive.
Interference fits are the exact opposite. They're designed to permanently lock parts together using immense friction.
So no gap.
No gap. To achieve this, the tolerances must be engineered so that any physical condition of the internal part is strictly larger than any physical condition of the external part.
So even if I happen to pull the absolutely smallest pin allowed by the drawing, and I try to put it into the absolutely largest hole allowed by the drawing, the pin is still physically too big to fit. They're mathematically designed to crash into each other.
Exactly. They cannot be assembled by hand. You have to physically deform the material slightly to get them together.
Like using an arbor press.
Right. You might use a press to physically ram a bearing into a housing, or for extreme interference fits, you use thermal expansion and contraction, a shrink fit.
Oh, I love shrink fits.
You take the steel pin and submerge it in liquid nitrogen to literally shrink its diameter.
Yeah.
You take the steel housing and hit it with an induction heater to expand the hole.
And then you work really fast.
You drop the frozen pin into the hot hole, and as their temperatures equalize to ambient room temperature, the metal expands and contracts back to its normal size, locking them together with thousands of pounds of radial force.
It's basically welding with temperature and friction.
Basically, yeah.
But whether you're designing a loose clearance fit or an extreme shrink fit, the geometry of these parts is rarely just a simple pin and a simple hole.
Right. It's never that easy.
We're dealing with complex gearboxes, engine blocks, and satellite chassis. To measure where all these holes and pins are located relative to each other, you need a starting point, an anchor.
Yes.
And this is where the concept of datums enters the conversation. Our sources emphasize datums relentlessly. Let's demystify them. What exactly is a datum?
Well, a lot of people try to use the analogy of a house foundation. They say a datum is like the concrete slab you build from. But a house foundation is essentially a 2D concept. It only establishes the floor.
Right, it's just one plane.
In mechanical engineering, we operate in 3D space, and every part has 6 degrees of freedom. It can translate, move up and down, left and right, forward and backward, and it can rotate, pitch, roll, and yaw.
Okay, so a datum needs to control all of that.
Exactly. A datum is a perfect theoretical geometric construct, like a plane, an axis, or a center point that we use to arrest those degrees of freedom and lock the part in space.
I've heard a much better analogy for datums. Think of pinning a delicate butterfly to a display board.
Oh, I like where this is going.
You have this complex three-dimensional object. First, you press its back flat against the board. That is your primary datum plane. It takes away 3 degrees of freedom. It can no longer move up and down through the board, and it cannot pitch or roll.
Right.
But it can still slide around on the board, and it can spin like a dial. So you push its side against a straight edge. That is your secondary datum. Now, it can't slide left or right, and it can't spin.
It's getting locked in.
It only has 1 degree of freedom left. It can slide up and down along that straight edge. Finally, you push the top of the butterfly against a final pin. That is your tertiary datum. The butterfly is now fully locked in 3D space.
That is an incredibly accurate mechanical analogy. What you just described is the fundamental 3-2-1 rule of datum reference frames.
3, 2, 1.
By establishing a primary, secondary, and tertiary datum, you lock the part into a theoretical corner. Once the part is completely immobilized in that perfect theoretical reference frame, then and only then can you start measuring the true position of every other hole, slot, and surface on the part.
Because now everyone agrees on exactly where 0 is.
Exactly. The datum reference frame serves as the universal anchor for the designer, the machinist, and the quality inspector. It completely eliminates the tribal knowledge ambiguity of where to measure from.
So on the factory floor, a theoretical datum plane isn't just an idea. It is simulated by physical equipment.
Right.
You take your physical, slightly warped, imperfect machined block, and you rest it on a massive, perfectly calibrated granite surface plate. That physical contact between the imperfect part and the perfect granite establishes datum A.
Yes.
Now, every height gauge measurement taken from that granite plate upwards is anchored to the exact same universal mathematical truth.
Exactly. The drawing tells the inspector explicitly, press this specific face against the granite, push this specific edge against the angle block, now measure the hole.
Okay, this raises a massive question for me, and I really want to push back on the psychology of design engineers here. Because if datums are this perfect universal anchor and they provide absolute mathematical clarity, why do we still see so many parts costing a fortune because the tolerances are insanely unnecessarily tight? Is it possible that most over-tolerancing, where an engineer demands a tolerance of 0.0001 inches on a non-critical part, is actually just a symptom of them fundamentally misunderstanding datums?
You have hit on one of the most common and expensive psychological failures in design engineering.
Yeah.
Yes, chronic overtolerancing is very frequently a symptom of datum panic.
Datum panic. I love that term. How does it happen?
Imagine an engineer is designing a long cantilevered bracket. They choose a very small, somewhat rough surface at the very back of the bracket as their primary datum.
Okay, a bad foundation.
A terrible foundation. Because that starting face is small and imperfect, it doesn't stabilize the part well. Any microscopic variation at that small datum face gets mathematically amplified the further out you measure along the bracket. It acts like a lever arm of error.
Oh, so a tiny tilt at the base means the tip is way off.
Exactly. The engineer runs a basic analysis in their CAD software, sees this massive amplified variation at the far end of the bracket, and realizes the mating holes aren't going to align.
And instead of stepping back and saying, wait, I chose a terrible foundation, let me pick a better datum structure, they panic.
They panic. They leave the bad datum in place, and their reflex is to just crush the linear tolerances. They demand that the machine shop hit impossible levels of precision to compensate for the shaky foundation.
So they demand aerospace-level precision on a bracket that just holds a sensor, totally skyrocketing the manufacturing cost.
Precisely. As the sources strongly warn, we must avoid over-tolerancing. A functionally logical datum reference frame one that mimics exactly how the part will physically bolt into the final assembly prevents the need for impossible precision.
Because if you anchor the part correctly, based on its actual physical function, you can absorb a lot of natural manufacturing variation.
You can absorb a ton of it. You can loosen the tolerances, save a massive amount of money on machining and inspection, and still mathematically guarantee interchangeability. Fix the foundation, and you can relax the walls.
That is a profound paradigm shift. Tolerances are tight because the foundation is shaky, but, anchoring a single part to a granite table only solves half the problem. What happens when you take 5, 10, or 50 of those perfectly datumed parts and try to bolt them all together in a single assembly?
The errors accumulate.
Exactly. And this brings us to the most technically dense, mathematically rigorous part of our deep dive today. The Boeing Research and Technology paper by Fritz Schultz on tolerance stack analysis.
This is where GD&T transitions from pure 3D geometry into the realm of statistical mathematics.
Yes, the heavy math.
When you are assembling a complex system, you are not just verifying individual parts, you are evaluating an assembly gap. We want to know if part A plus part B plus part C bolted together will still fit inside the main housing, or if the accumulated variation will cause them to crash.
And in Schultz's paper, the critical gap we are trying to evaluate is referred to mathematically as G.
Right.
And this gap G is usually just a function, often a simple sum or difference, of the individual detailed dimensions of all the parts in the stack, which Schultz denotes mathematically as Li. So the total length of the stack is L1 plus L2 plus L3, and so on.
Correct. And the entire discipline of tolerance stack analysis is about predicting what happens to that final gap G when every single one of those Li dimensions inevitably varies within their allowed tolerance zones.
Because they will vary.
Always. Schultz outlines two primary methods for calculating this, and they represent completely different philosophies of risk. Let's start with method one, worst-case analysis, which is mathematically referred to as arithmetic tolerancing.
All right, walk me through the worst-case scenario. Just how pessimistic is this math?
It is the absolute maximum level of pessimism. In arithmetic worst-case analysis, the engineer assumes that every single part in the assembly has been machined to the extreme absolute limit of its tolerance band.
Ouch.
Furthermore, it assumes that nature is actively conspiring against you, and every single part happens to be at the extreme limit in the exact same direction.
So if I'm stacking 5 steel plates, and the drawing says each plate can be up to 0.1 millimeters too thick, worst-case analysis assumes that the machinist didn't hit the nominal target on a single plate.
Not one.
It assumes plate 1 is exactly 0.1 millimeters too thick, plate 2 is exactly 0.1 millimeters too thick, and so on.
Exactly. You simply add all the individual extreme tolerances together using basic arithmetic to find the total accumulated maximum variation, which Schultz denotes mathematically as delta y.
Okay, so delta y.
In your example, delta y is 0.5 millimeters. You then design your main housing to accommodate that massive 0.5 millimeter worst-case growth.
But logically, that seems completely unsustainable from a cost perspective.
That is.
If I'm a project manager and my engineers are designing based on arithmetic worst-case scenarios, I am paying a fortune. The statistical odds of reaching your hand into 5 different bins of parts pulled from different manufacturing batches and randomly selecting 5 parts that are all simultaneously maxed out at the extreme upper limit of their tolerance.
The odds are infinitesimally small.
Right. If I force the machine shop to hold insanely tight tolerances on the individual parts just to make this worst-case sum look manageable on paper, I am bleeding the budget dry buying precision I don't actually need.
You have perfectly articulated the inherent flaw of arithmetic tolerancing in mass production. It is incredibly safe, but it is ruinously expensive. That economic reality drove the industry to adopt method 2, the RSS method, which stands for root sum square or statistical tolerancing.
Okay, so RSS brings the math back to reality. How does it work?
RSS acknowledges that manufacturing processes, when operating correctly, follow a normal distribution, a bell curve.
Right. Most parts hit near the middle.
Exactly. Most of the parts the CNC machine produces will fall right near the perfect nominal center of the tolerance band. A few will be a little larger, a few will be a little smaller, but the extreme limits are rare.
So it's about probability.
Yes. RSS uses the standard deviation denoted mathematically as sigma and the statistical variance of the manufacturing process to predict the stack.
So instead of assuming everything goes perfectly wrong in the same direction, RSS assumes a canceling effect.
Exactly.
If part A happens to be a little too thick, statistical probability says part B is likely near the middle, and part C might actually be a little too thin. They naturally absorb each other's variations in the final assembly.
Exactly. By taking the square root of the sum of the squares of the individual standard deviations, RSS provides a much tighter, more realistic prediction of the final assembly variation.
Which means cheaper parts.
Yes. Because the predicted assembly tolerance is tighter, the engineer can safely loosen the tolerances on the individual detail parts. Looser parts are cheaper to machine, cheaper to inspect, and you save massive amounts of money without sacrificing the assembly.
It sounds like the perfect solution. But the Boeing paper doesn't stop at basic RSS. Schultz throws a massive wrench into this clean mathematical bell curve.
Oh, the mean shifts.
Yes, he introduces the reality of mean shifts. And this is where I need you to clarify something, because reading the paper I got a bit confused.
Sure.
Tool wear is a physical, measurable thing, right? A carbide cutting insert loses a micron of its edge every time it passes over the steel. That is a linear, predictable, physical change. The tool gets shorter, so the parts slowly get larger.
Right.
Why on earth is Schultz treating a predictable physical degradation as a statistical variable that ruins the RSS math?
That is an excellent pushback. And it gets to the heart of why the Boeing paper is so important. You are right. The wear on one single tool cutting one single part is linear and predictable.
Okay.
But remember, we are talking about mass production aerospace supply chains. When Boeing orders 10,000 specialized fasteners, they aren't coming off one machine.
Right, they're outsourced.
They're coming from 5 different CNC lathes, operating in 3 different supplier facilities, running at slightly different feed rates, operated by different machinists who change out the dull cutting tools at different intervals.
Ah, I see. It's a chaotic system.
So when you aggregate all those parts into a single warehouse bin, the overall distribution of those parts, it's still a bell curve. But the center of that bell curve, the mean, is no longer perfectly centered on the nominal dimension.
Because tools wear down before they are replaced.
Exactly. Because of that, the average size of the parts tends to drift toward the side of the tolerance band that represents less material removal. That is a mean shift. The bell curve is physically sliding to the right or the left over time.
So you can't rely on pure basic RSS statistics because the fundamental assumption of RSS that the variations will randomly cancel each other out around a perfect center point is physically false. The deck is stacked in the direction of the tool wear.
Precisely. And this is where Schultz details the truly fascinating math of risk assessment. In traditional centered statistical analysis, engineers design for a plus or minus 3 sigma range.
Okay, plus or minus 3 sigma.
In a perfectly centered bell curve, this corresponds to an accepted failure rate of 0.27%, meaning they accept the risk that roughly 3 out of every 1,000 assemblies will statistically fall outside the limits and fail to assemble.
And they accept that tiny risk because it saves millions in manufacturing costs compared to worst-case tolerancing.
Exactly.
But wait, if the mean shifts, if the whole bell curve slides to the right because the tools are wearing down, doesn't that massively increase the failure rate on the right side of the curve?
It does push the curve into the upper limit. But here is the brilliant, counterintuitive mathematical revelation in the Boeing paper.
Okay, lay it on me.
When you take the worst-case mean shifts, assuming the tool wear on all the parts drifted in the absolute worst possible direction, and you stack those arithmetic shifts on top of the RSS statistical variability, the overall risk of random failure doesn't skyrocket. It actually drops.
Wait, how is that mathematically possible? You're adding worst case to RSS.
Because the risk is no longer spread across both extremes. In a perfectly centered bell curve, you have a tiny risk of failing by being too small, and a tiny risk of failing by being too big.
Okay.
But when the mean shifts severely to the too big side, the tail of the bell curve on the too small side gets pulled completely away from the lower limit.
Oh.
You essentially eliminate the risk of the assembly being too small. All of your risk is now concentrated solely on the too big upper limit.
That is wild.
Because you are only fighting one tail of the distribution instead of two, the total overall probability of failure essentially halves. The risk factor drops from 0.27% down to 0.135%.
The predictable physical reality of the tool wear actually eliminates one of the statistical failure modes, having your overall random risk to 0.135%.
That is brilliant.
It is brilliant.
So what does Boeing do with this information? Do they just enjoy a slightly lower failure rate on the assembly floor? No, an organization like Boeing uses that mathematical risk reduction as leverage. They use it to buy back even more tolerance for the machine shops to save even more money.
So they tweak the math.
Schultz explains that to seamlessly take advantage of this risk reduction while maintaining the traditional 0.27% failure target, they inject a specific mathematical correction factor into the RSS equation.
What's the factor?
The RSS portion of the part-to-part variation is multiplied by an exact factor, 0.927.
0.927.
Yes. By multiplying the RSS variation by 0.927, you artificially shrink the statistical variance prediction just enough to mathematically balance out the worst-case mean shifts.
Wow.
It allows the engineer to account for the gritty reality of tool wear while safely maximizing the allowed tolerances, all without exceeding the accepted failure rate. It is an absolute masterclass in blending the pessimism of worst-case arithmetic with the optimism of pure statistics.
But let's bring this down to the desk of the everyday engineer. If I'm sitting in front of my CAD terminal trying to design a gearbox assembly, how do I practically apply this?
Good question.
Do I run the ultra-pessimistic worst-case delta Y calculation and overpay for parts? Or do I run this highly complex Boeing RSS math with the 0.927 multiplier and risk that a mean shift might occasionally cause an assembly line jam?
Well, the Boeing paper actually provides a highly pragmatic, straightforward compromise for the working engineer.
Oh, thank goodness.
Schultz suggests that for critical gaps, you should actually calculate the tolerance stack using both methods.
Both of them.
Yes. You run the arithmetic worst-case stack to see the absolute physical limits. Then you run the modified RSS stack with the mean shifts to see the statistical probability.
Okay.
Finally, you take those two resulting gap numbers and you simply average them together.
It is brilliant in its simplicity. You just find the exact midpoint between absolute paranoia and absolute mathematical optimism.
Exactly. Averaging the two provides a highly robust, balanced tolerance limit that protects your assembly from catastrophic worst-case stack-ups, while explicitly preventing you from forcing the machine shop to achieve impossible budget-destroying precision.
That right there is the kind of practical engineering philosophy that saves companies millions of dollars. Calculate both extremes, understand the physics behind both, and engineer the middle ground.
Yes.
Now we are entering the final section of our deep dive today, and we want to deliver exactly on the mission we set out at the beginning. We're going to synthesize all this heavy mathematics and historical context to answer the most common burning questions people in the industry are asking right now.
It is the perfect way to wrap this up. We've covered the theory, but how does this apply to the rapidly evolving future of manufacturing technology?
Let's start with question one, which is a massive debate driven by software vendors. A lot of tech companies are pushing this concept of the digital twin, right?
Oh, yes, the digital twin.
So, will advanced 3D CAD, solid models, and AI eventually eliminate the need for GD&T altogether? Will the software just handle all the variation in the background without us having to define datums and tolerance zones?
The answer from the sources is an absolute, emphatic no.
Not going to happen.
The ASQ overview document explicitly addresses this software-driven utopian vision. It acknowledges that future technology embedded directly into solid models will absolutely change how we apply and process the rules.
Like automating the math.
Right. The software will enable fully automated tolerance stack analysis with a click of a button. It will allow for highly advanced FEA finite element analysis.
And for those who might not know, FEA is where the computer breaks a complex 3D shape down into thousands of tiny digital mesh blocks and mathematically simulates exactly how the part will bend, stretch, and distribute stress when physical loads and heat are applied to it.
Exactly. And future software will be able to run that FEA simulation not just on the perfect nominal part, but by actually simulating the maximum feature variation allowed by the tolerances.
Which is amazing.
It is. It will push the industry into a truly paperless, model-based definition environment. The physical 2D blueprint will die. But the concept of toleranceless design, the idea that the software will just figure it out on its own, is a massive, dangerous misconception. The source is incredibly blunt about this. It states, and I quote, "Toleranceless design, no way," complete with multiple exclamation points.
And you cannot code away physics.
Exactly. The 3D digital model is perfect. It is dimensionless math in a void. But the physical CNC machine cutting the steel is not perfect.
Right.
The tool will still wear down. The titanium will still warp when it gets hot during machining. The spindle will still vibrate. The rules of GD&T, the datum reference frames that establish the physical anchor, the geometric tolerance zones that define acceptable limits of physical form, those rules must fundamentally exist.
Even if they're invisible.
Yes. They will exist as invisible metadata attached to the faces of the 3D solid model, rather than symbols printed on a piece of paper. But the engineer must still actively define the functional limits of the hardware. The software will automate the math, but it cannot invent the design intent.
Which perfectly sets up question two. Who actually needs to use GD&T in the modern era? Is this strictly an aerospace thing for people building rockets at 10,000 a pound? Or does the engineer designing a mountain bike suspension hub need to use this complex language too?
It brings us entirely back to that core philosophy of interchangeability.
Right, the rocking horse versus mass production.
The sources are clear. If you are a craftsman hand-fitting a custom assembly, or if your entire product is machined by one guy on one lathe who checks the fit of every part manually, you do not need GD&T.
Save yourself the headache.
Exactly. But if you are manufacturing at any kind of scale, it is mandatory. Whether you are building space station components, mountain bike hubs, or consumer blenders.
Because of the supply chain.
Yes. If you rely on a decentralized supply chain, where the housing is cast in Mexico, the gears are machined in Germany, the bearings are bought off the shelf from Japan, and it is all bolted together in an assembly plant in Texas, GD&T is the only legal mathematical language that guarantees those parts will fit.
Without tribal knowledge.
Exactly. It is the only way to mathematically guarantee interchangeability across language barriers, time zones, and different manufacturing processes.
And that leads us to the ultimate question, question 3. How do we fix the Houston, it doesn't fit problem today?
Actionable advice.
Right. If a project manager listening to this right now is struggling with massive scrap rates, parts that won't assemble, and vendors arguing over inspection reports, what is the immediate, actionable prescription based on these sources?
The prescription requires a hard reset of the engineering culture. First, you must immediately and systematically eradicate tribal knowledge.
Write it all down.
Yes. If your quality inspector or your machinist has to walk over to an engineer's desk to ask what a specific dimension actually means, your documentation system is fundamentally broken.
Agreed.
Second, you must adopt and ruthlessly enforce an internationally recognized geometric standard. The sources highlight ASME Y14.5 2 out in 18 as the gold standard for robust functional design.
And as we learned with the 65% problem, you can't just assume everyone knows you're using it.
Absolutely not. Step 3 is explicit verification. You must explicitly state which standard, including the specific year of revision, governs every single dataset, CAD model, and drawing you send out.
Right. Tolerances per ASME Y14.5 2018.
And you must actively verify that your supplier's CMM software is set to calculate using that exact same dialect. Do not let wrong is best hide in the software defaults.
Audit the software.
Audit everything. And finally, you have to elevate your engineering department's mathematical rigor. They must understand whether a specific critical interface requires a rigid, worst-case arithmetic stack analysis, or if the company can save massive amounts of capital by utilizing statistical RSS methods with the proper Boeing mean shift multipliers.
It is about moving from an attitude of hoping the metal fits to an attitude of mathematically proving it will fit before the purchase order is even signed.
Precisely. It is about total intentionality.
Which brings me to a final thought I want to leave you with, something to genuinely mull over the next time you're staring at a complex 3D model on your screen or just walking the floor of a machine shop.
Look here.
Ultimately, GD&T is not about demanding absolute perfection from the tools and the humans that make our parts. In fact, it's the exact opposite of that.
It is.
It's an incredibly brilliant, globally evolved mathematical framework that exists solely to allow for human imperfection. It's a system that accepts that tools will dull, metal will warp, and machines will vibrate. And yet, it still guarantees that the final complex machine will bolt together and function beautifully.
That's a great way to frame it.
It makes you wonder, is the true highest art of engineering not the pursuit of perfection, but rather the absolute mastery of acceptable flaws?
That is a profound perspective. It is the rigorous science of knowing exactly how imperfect you can afford to be and building a world that works perfectly within those boundaries.
If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.